All right, so we're going to get into two-sided limits today. But before we start back on to limits, I want to review a couple topics that are going to be helpful in being able to solve two-sided limits, okay? And one of the things that I want to review is synthetic division, okay? So let's say we have this fraction here. We have this monstrous polynomial on the top being divided by the binomial x plus 4. Note it is a linear binomial. It is x to the first plus 4. If this was x squared plus 4, we could not use synthetic division. The good news is that in limits, if we're going to use synthetic division on limits, we're in the convenient situation of always dealing with a circumstance where we have a linear binomial, but we'll get to that later, okay? All right, so let's say that we wanted to divide x plus 4 out of this huge polynomial, okay? So remember, what we would do is we would have to take the 0 of this x plus 4, which is basically the opposite of whatever this number is. So this is plus 4, so we would take the value negative 4 and we would put it in what we call a half box, right? Then we're going to take all of the coefficients, starting with the highest power and then going down by each subsequent power. So we need the coefficient of the x to the fourth power, which is 3. Then we need the coefficient of the x to the third power, which is 5. Remember, we don't need variables in synthetic division. We just need their coefficients. Then we have negative 26. Then we have 13. And then we have the constant 20. Now, I also want to remind you that if we skipped over a power, so if we didn't have plus 5x cubed here, we would put a 0 in the place of that particular power, okay? So then we're going to draw a horizontal line, and we want to leave space because we're going to write some numbers in here, right? And then what we're going to do is, now this is my personal procedure. You may have learned it a little tiny bit differently, but it still results in the same effect. I always start off by putting a 0 under the first number. Now I'm going to add, right? So 3 plus 0 is 3. Then we take whatever number we put down here, the sum down here, and we multiply it by the half box number. 3 times negative 4 is negative 12. And we put that above the line in the next column. Now we're going to add negative 12 plus 5 is negative 7. Now we're going to multiply. Negative 7 times negative 4 is 28. 28 plus negative 26 is 2. 2 times negative 4 is negative 8. Negative 8 plus 13 is 5. 5 times negative 4 is negative 20. And negative 20 plus 20 is 0. And this last number, we always box that off. That is the remainder. Now, I created this problem to have a remainder of 0 conveniently. But what you're going to find is that in dealing with limits, you are always, or you should always, result in a remainder of 0. And that brings up a concept that we've learned previously called the factor theorem. Now, I'm not going to get into the factor theorem here, but you could benefit by looking into the factor theorem and seeing how it relates to limits, okay? All right, so now these numbers down here, they represent the coefficients of the quotient, okay? So when we divide x plus 4 out of this polynomial, we're dividing by x to the first power, so the x to the 4 divided by x to the first becomes x to the third. So this polynomial is going to start with x to the third, okay? We always reduce our power by 1. So this is now going to become 3x to the third power. That's a little ugly, sorry about that. X to the third power minus 7x to the second power. So if this is the third power coefficient, this is automatically the second power coefficient, first power coefficient, and then the constant, okay? Now plus 2x and then plus 5. And so what we can now actually say, since this is the quotient, we can actually say that this polynomial, if we were to put some parentheses around it, and then in front of here, we could then put x plus 4, and we could say that x plus 4 times this polynomial is equal to this polynomial in the numerator, okay? And so that is just our review of synthetic division. You're probably going to use a good bit of synthetic division to solve several limits, okay? Now let's move on and let's review a concept from rational functions called wholes. All right, so now we're going to review wholes in rational functions, okay? So the idea goes like this, is that if we were to take a rational function, and let's say we were to factor it, okay, so if you look at this rational function just for a second, you might see that there's something that we can do algebraically to simplify this function, right? And that is we can cancel out this binomial x minus 3, because the numerator has an x minus 3 and the denominator has an x minus 3, okay? Now, if we were to cancel those, we would end up with x plus 7 over x minus 1. But x plus 7 over x minus 1 is not the exact same function. It looks the same on a graph, and in all other ways, it's identical to this function here. But this function, you are not allowed to plug in a 3. See, this function right here, anytime you have a denominator, if a number will make the denominator equal 0, we know that is not on the domain of that function. So we know that x cannot equal 1, and x also cannot equal 3. And remember that we learned in pre-calculus that if we put any of these numbers that are not on the domain, if we plug them in, that if we get 0 over 0 as a result, that's not an answer. That's just an indicator that there is a hole in the function. Okay, so if I were to plug, or that there may, I should say, that there may be a hole in the function. Okay, so if I plug this 3 in here, up here, 3 plus 7, that's 10. 3 minus 3, that's 0. 10 times 0 is 0, right? Plug it in here, 3 minus 3 is 0, 3 minus 1 is 2, 0 times 2 is 0, so I have 0 over 0. This indicates that f of x may have a hole in its graph. Well, holes are a regular feature in dealing with limits in calculus. That's why I'm reviewing holes with you right now, okay? So here's the idea. One of the things that we learned in pre-calculus is we learned how to identify where the hole is. What are the coordinates of the hole, right? So there is a hole at some x, y coordinate on the graph, okay? And what a hole looks like is, let's say that we have a graph of something, right? And let's say, I don't know, let's say that it's a curvy graph, and let's say there's a hole at this x value. Let's say at an x value of 2, there's a hole. That it would look something like this. This is how we often represent it in mathematics when we're drawing it. What we do is we eliminate a portion of the curve and we draw in an open circle. That indicates a hole in the function, okay? All right, so what we want to know here is, what is the x and y, what's the x coordinate and the y coordinate of that hole? Well, it's easy to find the x coordinate because it's whatever number you're plugging in to get 0 over 0. So in this particular case, we know that there's a hole at x value of 3. So now what we need to do is we need to find out, well, what is the y coordinate of that hole? Well, I taught you in pre-calculus that all you have to do to find the y value of the hole is you can cancel out the x minus 3 in the numerator and the denominator, and now plug that 3 in here and in here. And if we plug in the 3 here, we get 3 plus 7, that's 10. And then plug the 3 in here, 3 minus 1, that's 2. And so the y coordinate is going to be at 10 over 2. 10 divided by 2 is 5, and therefore this function has a hole at the coordinates 3, 5. Okay? And that procedure, that I just reviewed, the idea of identifying the location of a hole, is useful when we learn limits, because oftentimes you're going to be asked to find the limit of a function where there's a hole. And since the limit is always the output value, that would mean in this case, if I wanted to know the limit as x approaches 3, the answer would be 5. Okay, but we'll get to that a little bit later. And now we're just going to do a quick review of factoring. All right, so now let's just do a quick review of factoring. Now, typically with factoring, there are a couple different kinds of factoring, and we may use any or all of them in learning about limits, okay? So let's say that we have this rational function here. You can see it has a quadratic in the numerator and it has a quadratic in the denominator. And let's say that we wanted to identify a hole in this particular function. So we'll take our review of holes that we just did and we'll combine it with our review of factoring, okay? So do you recall that when you want to if you want to try and identify a whole, one thing that you can do is you can factor the numerator and the denominator of the rational function, and that'll help you see what it is that you want to cancel. It can help you see which number that when you plug it in, it causes the rational function to be 0 over 0. Okay, and so we're going to factor the numerator here, and I don't know if you remember, this is a difference of squares, right? And whenever you have a difference of squares, we have x squared, then we have a minus, then a number over here, that all you have to do is take the square root of this and then the square root of this, and you wind up with two of them, right? One of them is plus and one of them is minus. So this difference of squares, it factors into x plus 3 times x minus 3, okay? X squared minus 9 is the same thing as x plus 3 times x minus 3. That's just our quick review of how to do a difference of squares, okay? If you need more review than that, you may want to go find my videos from college algebra, where I do several videos on a bunch of different kinds of quadratic factoring, okay? This one here, what we're going to do is we're going to do a product sum factoring here. This is a situation where all we have to do is find two numbers that multiply to 12 and add up to 7, and then those are the numbers that we'll wind up having in the two binomials. So we'll start off with an x and an x, and then two numbers that multiply to 12 are 4 and 3, because positive 4 times positive 3 is 12, and if you add positive 4 and positive 3, 3 plus 4 is 7, and therefore our two numbers are positive 4 and positive 3. So we'll put plus 4 for positive 4, oops, that's an ugly 4, and then plus 3 for positive 3. And now we can clearly see that the numerator and denominator both have an x plus 3, and that now indicates to us what the x value is that is going to cause the whole. The number that plugs in to x here and makes this 0, and if it's plugged in here it makes it 0, that is the x value of our whole. So we know that there's going to be a whole at, all right, and if the number that we plug in here is negative 3, right? Negative 3 plus 3 is 0. Negative 3 plus 3 is 0, so we'd have 0 times this is 0, 0 times this is 0, and we have 0 over 0. So we know that there is an x, or there is a whole at x coordinate negative 3. Now, you might be asking, what about the negative 4? Isn't that a problem? Didn't we learn that in pre-calculus? Yes, but because putting in a negative 4 will not give us 0 over 0, it'll give us some number over 0. In fact, what number? Negative 4 squared is 16 minus 9 is 5. So if we plugged a negative 4 in, we would get 5 over 0, but that indicates a vertical asymptote, which is also important in limits. Remember that a vertical asymptote would indicate that the limit does not exist, okay, that we're either going to positive infinity or negative infinity, okay? And we'll talk about that more in today's lesson. All right, so now in order to find out the y coordinate of the whole, we would cross out the x plus 3 and then plug the negative 3 in here. So negative 3 minus 3, that's negative 6. Negative 3 plus 4, that is 1, and so negative 6 over 1 is negative 6. And therefore, this function has a whole at negative 3 and negative 6, okay? And so that's our review of factoring, and then we just did a little bit of an extra review of wholes. The last thing I want to say is we reviewed synthetic division at the beginning of this segment, and I want to remind you that synthetic division is basically just a more complicated form of factoring. And the reason we reviewed synthetic division is because we want to use synthetic division to factor functions to be able to identify where the wholes are. That's the whole purpose of this review. Now what we're going to do is we're going to move on to understanding two-sided limits.